questions. I should also like to thank Radius for sponsoring me to be here today. My presentation today, I'm going to first of all put PE pipelining systems into wider context of pipeline rehabilitation and talk a little bit about pipeliner classification. That's because that will feature quite a bit in the presentation. I'm then going to get on to the meat of the presentation, which is about the technologies themselves. And those of you who have any familiarity with this area of technology will appreciate that I've had to make a lot of generalizations in order to cram a great deal of information into a small space. I think the subtext or the subtitle to the presentation should have been that there's always an exception, and I'm sure you'll see them. I will talk a little bit about pipeline, host pipeline preparation as part of that, and then get on to talk about PE liner pipe design, and then at the end, some frequently asked questions. Well, certainly some questions that I was frequently asked during my career, and I thought I would give you the answers to them today so you don't have to keep telephoning us. Okay, moving on into the place of PE pipelining within the wider context of pipeline rehabilitation. This forms part of the family of insertion lining systems, so we're essentially talking about using an existing host pipe which you're going to put some sort of liner pipe into. I'm not going to be talking about segmental linings nor spirally wound liners or some of the other profiled liners that Derek mentioned previously, because these are predominantly used for gravity sewer applications, and as you will see as I go along, the principal use of PE pipe lining is for lining pressure pipes. Okay, classification of liner pipes. I'm going to be using these terms fairly frequently, just to bring you all up to speed. Structural liner pipe is one that can tolerate all of the service loads that are going to be applied to it throughout the course of the design life. That includes both the internal pressure and external loads, including such things as soil column, surcharge, and external hydrostatic pressure loads. An interactive liner is one that relies on the structural strength of the host pipe to provide the primary pressure containment envelope for the lined pipe system. The liner itself simply acts as a membrane inside that to cover over holes or perhaps leaking pipe joints which might be present either initially at the time of the installation or which might appear during the course of the design life of the rehabilitated pipeline. And then finally, non-structural liners are those typically spray-applied resins which are used principally to prevent the re-corrosion of cleaned cast iron or steel pipes. Liner system classification. Now we often get muddled up with this, but it's very straightforward really. The classification, whether it's structural or interactive, depends principally on the relationship between the specification of the liner, and that's simply a product of the pipe wall thickness and the material strength. It's the relationship between that and the pipeline operating pressure. So to give you a couple of examples, an SCR 17 P100 liner pipe, which has a water rating of PN10, if you use that for lining a pipeline that's operating at 8 bar, it's going to be structural. But that same liner may well be used for lining a water injection pipeline for the water industry, for the oil industry, beg your pardon, for the oil industry, and that pipeline might be operating at hundreds of bar, and in that case the same liner is an interactive liner. Similarly, you could look at thin wall P liners. SDR 33 P100 liner pipe will have a natural pressure rating, 50 years of PN5 for water. Use that in a close fit interactive lining application in an 8 bar pipeline, and that requires the support of the host pipe. It's interactive, but it does have its own pressure rating in its own right. So if the pipeline operating pressure is normally 4 bar or less, for example, that would at least be fully pressure capable throughout its life. There are a number of systems that are used for classifying lining pipe systems. This is one that was developed by ISO and SEN, and PE pipe lining systems fall into the Class A and Class B category. Class A is fully structural, and one of the key features of that is the top line. The lining system has to be able to survive the complete failure of the host pipe, including instantaneous fracture. Okay, if I can make this move on. So I'll now move on to the technologies themselves, and for my own convenience I've split these simply into loose fit PE lining techniques and close fit and all of the other specialist lining techniques as a separate branch. And there are a number of subcategories you'll see as we go along. Loose fit PE lining is the simplest and the most common form of PE pipe lining, or the use of PE pipe for lining existing pipes. Very simply stated, you take a PE liner pipe that has an outside diameter that is smaller than the inside diameter of the hose pipe you're going into. You tend to use, it will be a fully pressure rated pipe. The pipe is either welded into long strings on site if it's delivered in the form of sticks, it could or it could be delivered in the form of coils and inserted. It's normally winched into place, towed into place, but there are devices which have come onto the market in the past few years which enable you to even push loose fit liners into place. These are available up to about DM400. And there are other technologies available for dealing with drains. I won't go into those in any detail. There is a wide range of PE pipe sizes available to choose from. They are standard sizes, they're in the international and national standards. Mike will be talking about those later. It's quite a quick installation method. One of the most important features is that you use, because of their standard pipe sizes, you're using standard pipeline fittings, and that will always make it a very cost competitive solution compared to some of the others that I'm going to be talking about later, with one exception. The other drawbacks with PE slip lining are that you need long lead-in trenches in order to respect the minimum radius of curvature of the PE line pipe during insertion. It's important to avoid the risk of buckling and kinking of the liner as it goes into place. And of course, in order to remake customer service connections, you have to dig onto the pipe. There are methods perhaps being developed, but really it's still the old manual solution that is required, and in urban situations that can involve quite a lot of excavations, as you can see there. The big drawback with loose-fit polyethylene slip lining is the loss of cross-section capacity you get. There is, incidentally, the annular space which you need to think about. This can be a conduit for groundwater which can drag fines into the main and cause ground instability. So sealing the ends of the pipe is generally adequate with some fill the annulus at the ends. But being a flexible pipe, as one of my mentors told me many years ago, it's a flexible pipe. You don't need to grout it in place. It's probably best to let it flex. The reason that the close-fit lining technologies were developed was really on the back of the gas industry. Gas flow, much more so than water, gas flow is a very sensitive function of cross-section diameter of the pipeline cross-section, and it's more than the square of the diameter. That led to an interest in finding ways of maximising the capacity of P-lined pipes, and spawned a whole raft of technologies for close-fit lining. Now, these can be broadly split into two categories. There's a concentric reduction type and the folded systems. The most important thing to recognise is that most of these are just simply modified PE slip lining processes. So everything you know about laying PE pipe, everything you know about normal slip lining of PE apply in this case. It's just that there are some additional processes to reduce the diameter and bring it back to size to make it a close fit. To go through each of these branches of technology, and this is going to be a quick gallop, the first is concentric reduction, and there are a number of subgroups underneath that, but there are some basic principles. The basic principle with concentric reduction is that you start off with a PE line pipe which is slightly larger than the ID of the hose pipe you're going into. What that means is quite often you can use a standard size of PE pipe. That's important because you can get it from stock, quite often. The process somehow reduces the outside diameter to a smaller diameter than the ID of the hose pipe, and then the liner pipe can be taken in as a slip lining operation, either with or without applied tension. Once the liner is in place, it's then reverted to a close fit, either by releasing tension if it's one of those systems, or by hydraulic pressurization with cold water. Now I'm going to risk running an animation for you to just illustrate the point. The couple of key points here. PE pipe lining, you need an insertion pit and a reception pit, so you dig onto the main in two places, cut out sections of the hose pipe. The hose pipe has to be prepared, take out obstructions, clean it out, and then the liner is inserted. This is Subterra's subline DR process, previously known as roll down, where the liner pipe is pushed through sets of rollers which squeeze the diameter down, and that reduced diameter remains stable as you insert the liner pipe. The towing head's fitted on, the liner pipe's towed into place. Once it comes into the reception pit, it's pulled through sufficiently far to enable you to cut off again a little bit ahead of myself, to cut off the towing head. I've got a long way to go and a short time to get there. Cut off the towing head, fit an end termination which for the subline DR enables you to fill the liner pipe with cold water and pressurize it in a series of steps to bring it to a close fit. That's what that's showing here. Okay, I'm just going to try to accelerate matters there. Okay, so that's just a brief illustration. There are two families of concentric reduction technologies, roller reduction and die reduction. We've already looked briefly at the subline DR process, pushing pipe through sets of rollers, reversion by hydraulic pressurization. That technology is available in sizes from 100 to 500 millimeter pipe outside diameter, and can be applied to liner pipes in the range SDR11 to 33. The actual size depends on the diameter. Bends we're going to talk about later, lengths we're going to be talking about later. Typically you'd be using this to insert 300 meters at a time, because that tends to be the spacing between significant utility features like bends, tees and valves, which are used as insertion points. I should like to mention Radius has recently developed a technology demonstrator for a factory rolled down product, one that is actually delivered to site in the pre-reduced state. The technology is certainly available for 6-inch diameter, starts out life as DN155 SDR21. The factory roll down brings it down to 143 SDR17, so it can be coiled, and it's ideally suited to lining 6-inch cast iron pipes, which actually fall very awkwardly in terms of diameter between two different standard polyethylene pipe sizes. In Situ Form had their own version of this technology called In Situ Flex, in which the process was carried out by driving the liner pipe through driven rollers. It's no longer available in the UK, but I think still is available. It's still used in North America. Size is 100 to 250 diameter. Talked about the reversion. If we now move on to the die drawing technologies, The one you'd probably be most familiar with would be swage lining. This is, again, an on-site reduction process, and that involves pulling the PE liner pipe through a static ring die, and that reduces the diameter whilst it's under tension. You can pull the liner pipe into place, still under tension. Once the liner pipe is fully honed, pull it sufficiently far through to allow the liner to relax. When you release the tension, the liner relaxes longitudinally and expands diametrically back towards its original diameter. And that's been used in sizes up to 1200 millimetre diameter. There are fairly significant forces required to resist. There are very significant forces involved in the process, and there can be substantial groundworks and temporary works that need to be put in place to take those. The other the other die drawing system is the United Pipelines tight lining technology. This is very similar to swage lining, but instead of using a static ring die, it uses rings of rollers in a series of reducing diameters to achieve exactly the same effect. And we're looking at sizes up to 1300 millimetre diameter. It's very popular in the oil industry for lining water injection lines. Now moving on to the folded liner systems. Again, they can be broken down into a number of branches, but again, there are key principles. These are them. First of all, unlike concentric reduction, in the folded liner systems, you start out with a liner pipe which has a smaller outside diameter than the inside diameter of the hose pipe you're going into. And the reason for that is to ensure that when you open the liner pipe up, the fold deploys completely and the liner pipe comes to a circular form. The folding normally goes into a C or a U shape. That makes it easier to get the liner pipe into the hose pipe, and actually enables you to get around some more sharper bends. Hot formed factory liners, that U shape is retained without the need for any additional constraint, whereas the cold folded liners, they might be folded either on site or in the factory. They need some form of strapping to prevent the liner shape opening out and causing a problem. Once the liner's slip-lined into place, the ends are opened out and the shape is reformed, and that could either be with a combination of steam and or air pressure for the hot folded systems, or it could be by cold hydraulic pressurizations for the cold folded systems. Okay, I think we'll skip over, no, let's just, I can't find the arrow, here we are. So this again, it just illustrates, it requires two pits to be cut in the ground and break into the pipe in 2 points, an entry and a reception pit. Pipe has to be cleaned out, any obstructions removed. The liner pipe is then fed through the machine which folds the liner into the U shape. The shape is retained with straps. Towing head is fitted. The liner pipe is then drawn into the hose pipe. Once the liner pipe is in position, sufficiently inside the reception pit, the head is cut off. We'll get there in a moment. I'm going fast, and it is. Cut the towing head off, re-round the end of the pipe, fit an end termination which enables you to blank the line off, so it can be, in this case, filled with water and pressurised gradually to break the bands and bring the liner pipe to a circular form. It's important that the liner is filled completely with water. You don't really want air in it while you're doing the reversion, for reasons Derek explained earlier. Okay. Again, it's really naming of parts, so what technologies have been available are used. There's the site-folded systems. This is the one that I'm most familiar with because that's Subterra's offering throughout over the last 20 years or more. It's an on-site cold folding process using thin wall liner pipe. I've said all that before. It's available in a wide range of sizes, up to 1500mm diameter. The reason for that is that the equipment is bulky but simple. You process thin wall PE liner pipes using this process, and the reason for that is to avoid overstraining the PE pipe wall in the process. So SDRs from 26 to 80 are the complete range, but it's normally SDR 33 to 61. The folded shape, that U, makes it easier to go around bends. We'll talk about that later. Lengths we'll talk about later. And remember what I was saying about liner pipes can be structural or interactive, and it really just depends on the SDR of the liner and the operating pressure of the pipeline, whether it falls into the category of interactive or structural. Here's a slide which shows the subline ends being prepared for termination and the being flanged off for the reversion process. There are folded liner systems prepared in the factory. Two of these, subcoil and compact slim liner, were popular in the late 90s, early noughties. They've fallen into disuse recently, but there are still quite a bit of this in the ground. It's really a factory version of what I've just shown you for the normal site-applied subline. Because of the amount of liner pipe you can get on drums, the size range was restricted to 75 to 225mm diameter. I've included Primus line here. You may have seen this before, I don't know. This is a PE-coated and lined Kevlar reinforced flexible hose liner. It's extruded in the factory and reeled onto drums in a flat form. When it gets to site, there's usually a little bit of extra folding and taping to get the liner, make it easy to get the liner into place. It's available in sizes from 150 to 500, but it's in a series of discrete steps. So whether you get a close fit depends on just what size of hose pipe you've got. It may be more or less close fit, it may be more or less loose fit by the end of the day. Installation lengths up to 2.5 kilometres have been claimed. That's because you've got the Kevlar reinforcement inside it, and because it's a nice flexible liner, it will go around some decent bends. Ratings up to 30 bar in the small sizes. The rating goes down as the size increases, although you can get higher pressure ratings if you pay for more reinforcement layers. Of the factory hot folded systems, compact pipe U liner is probably the most well known. Compact pipe is probably the most well known. This is manufactured by Wavin, extruded round in the factory and then folded, taken to site on drums, peeled off, put into the hose pipe, ends opened out, and it's returned to round by a combination of steam and compressed air. Its size is 100 to 500mm diameter, and the upper diameter being limited by the sensible amount commercially of the liner pipe that you can get onto a standard transport drum. And there have been other technologies like thermopipe used, which also fall into the hot folded systems category. Not available now, but again, there's this product in the ground. Now, you can talk about liner pipes themselves, but in order to turn them into a system, you have to have connections. This is lost sight of it can be lost sight of. I've seen it in the past, with academics just looking at means of making liner pipes, but you have to have end terminations, and they have to be suitable both for installation at the time of the liner installation, but also for retrofit applications when you need to go back and make connections. The key issues for connections is that for close-fit liner pipes, you're going to be dealing with a non-standard OD, and for interactive liners, you need to support them over the entire length against the internal pressure. The solutions include both fusion, which tend to be used predominantly for solid wall structural PE liners, and mechanical, which are used both for structural and interactive, and also for solid wall and the specialist reinforced hoses. In terms of the fusion systems, it's important to respect the pipe diameter tolerances required for making electrofusion connections if you're going to use standard EF couplers. And for mechanical fittings, here what you're doing is using you may be either using the polyethylene itself, squeezing that between two rigid surfaces to make the seal, or by squeezing an elastomeric gasket onto it to make the seal. The important thing to recognise with mechanical joints for PE is that the PE tries to run away from any loads that you put on it. So the design of the fitting is very important. For structural PE liners then, what we can use as standard fittings, providing we can expand the line pipe up to the next standard size of PE pipe. Providing that's less than 10%, you can put a stiffener insert inside it and then make a connection, either mechanical or electrofusion, in much the same way. In terms of the customer service connections, fortunately these days the pipe manufacturers have developed ranges of electrofusion tees which are range rated, diameter range rated, so it's quite easy to deal with that situation. For the interactive and for specialist liners, for interactive liners, it's support over the entire length, and you need system-specific fittings for these, and it's important that the supplier understands the requirements as well. There are proprietary fittings available on the market now, and the same thing applies for customer service connections for interactive liners. Just a brief mention of one of Radius's developments, the Minimus EF branch saddle. This fits quite well into this area because the fitting itself is made to a bespoke internal diameter, so that it can be fitted precisely onto, say, a close-fit PE liner pipe, as well as an existing standard pipe, size pipe. There's a range of outlet sizes available for that too, very useful. Right, hose pipe preparation, there's not much to say about this, thankfully. First of all, you get rid of anything sticking into the pipe that might damage the liner pipe. You need to clean the pipe, typically scraping and plunging is enough to do that, followed by CCTV to make sure there's nothing in the way. If that looks okay, the next thing to do is to pull a proving piece of the same size of liner you're going to use through the pipe, check whether there's any damage. If that damage exceeds 10% of the wall thickness of the liner pipe, start again. You've got to look for where the damage is occurring, take it out and do that again. Once the damage is less than that 10% limit, you're safe to start. Applications, Norman's going to be talking about case studies, but PE pipe lining, PE liner pipes have been used across a wide range of industries. I'm now going to attempt to cover the area of PE liner pipe design, so I hope you will forgive me if this is fairly quick. We've talked about structural classifications of the liner pipes, the difference between interactive and structural, how you decide on that. I just wanted to make the point on the bottom here. PE pipe is usually uneconomic for lining gravity sewers, and that's because of the design thickness that is required to withstand the standard external hydrostatic pressure heads, but also this is about long lead-in trench lengths for sewers that are very, very deep, 5 metres, for example. They can be very significant. In terms of PE liner pipe design, then there's lots of sources available, and anything you know about PE pipe for direct lay and for slip lining also applies. So there are national standards like EN 1295 that tell you about what loads that need to be applied. You may not need to apply them all if you've got the support of the host pipe. You need to think about that. There are standard texts like this book from Janssen. There's even the pipe manufacturer's guidance, and there are actually company-specific procedures that are used for designing PE liner pipes, particularly in the oil industry. The additional design issues for liner pipes are the winching in forces, which you don't have to deal with elsewhere, There's buckling collapse, which needs to be considered, and that could apply to both interactive and structural liners, depending on the application. And there's hole and gap spanning, which is specifically for interactive liners. Derek's already mentioned something about PE, the properties of PE. PE is a viscoelastic material. What this means is if you apply a load to it, it extends elastically immediately, but then it tends to creep. And if you release the load, the material doesn't recover to its original length. And you can think of a good model for thinking about polyethylene and the way it behaves mechanically is to think of it like a bundle of spaghetti. And that kind of controls the response of the PE to different parameters. So for example, strain rate. High strain rates, the chains aren't able to do anything other than strain and stretch until they snap, and you get one characteristic strength. But if you do a long-term test like Derek was describing, you would obtain a lower strength. This is why you have a long-term design value of 8 megapascals. Temperature has an effect in the sense that at low temperatures the chains are frozen in position. It's very difficult to get them to move, so you get one strength. As you increase the temperature, the thermal motion of the molecules means that they can slide over each other much more readily, so you get a different characteristic strength at high temperature. And the environment itself can have an effect. Utility water, utility gas doesn't affect it, but if you're considering using it for oil industry applications like crude oil, the hydrocarbons can actually enter the structure and basically lubricate the molecules, allow them to slide over each other, and you get, again, a different characteristic strength. I said I'd talk about 3 things. Winching in force is first of those. The winching in force, very simply, it's the product of the weight of the pipe times the coefficient of friction. So the weight is cross-section area times the length times the density of the material. And that has to be less than the available strength in the liner pipe, which is the tensile property of the material times some sort of safety factor, again, times the cross-section area. So you think, well, what could possibly go wrong with that? It's very straightforward, isn't it? Yes. Well, the thing is that the tensile properties of PE depends, as I said, on the temperature and the load application time. Now, here's an example that we looked at recently, and thanks to Loic over at the back for this. The client had a 10-inch steel pipeline in the ground. You can see that there, some nice sweeping bends on it, and he wanted us to put a DM 110P liner pipe inside that. Well, that's going to be easy, isn't it? Well, not really. What you can't see, or unless you've got infrared vision, is that that pipeline is one of 4 carrying crude oil, which has raised the ground temperature to 60 degrees centigrade. And the client told us that the inside temperature of the pipeline was at least 50 degrees, was a maximum 50 degrees centigrade. But he wasn't going to allow us to look inside the pipeline until we actually turned up on the day ready to do the lining pipe job with our liner pipe. And that 50 degrees centigrade meant that the strength of the polyethylene was going to be about 40% lower. So you'd say, well, why not just string all the liner pipe out into one go for 950 metres and horse it in as fast as you can so that the liner pipe's in before it realises what's happening. Can't do that because this whole area is a triple SI, and we're only allowed to go on those yellow squares. Okay, you'd say, well, why not put it bring it on site in drums, haul it through a line tamer, weld another section on, pull that through the line tamer and keep going. Well, you couldn't do that either. The line tamer at that size takes over 800 kilos. The predicted insertion load was going to be 2 tons, and we only had 2.7 tons to play with. So in the end, we got a dispensation to lay out 100 metres at a time and haul that in. What that meant was you were pulling in for only 10 minutes at a time, which meant you were looking at a short-term load application, so a higher strength, but it was certain sure that with the welding to make up the 950 metres, you're going to be hauling in the pipeline over for over 8 hours. There's no doubt that the liner pipe was going to get up to temperature. Thankfully, we got it in, and it wasn't quite, the temperature wasn't quite as high as expected, but it had to be allowed for. Buckling collapse is the second design parameter I wanted to talk about. In direct lay pipelines, you're looking at a double lobe collapse situation. This is, those of you who are structural engineers knows that's Timoshenko or Lusher equations. But in a close-fit lining situation, you have a single lobe buckling mode to contend with. In order to create a buckle in a close-fit liner, the shoulders have to push out. That's what I've tried to show in that middle diagram up there. And that pushing out is resisted by the hose pipe, and that significantly enhances the resistance of the liner pipe to buckling collapse. But that enhancement factor is reduced if there's any disparity between the liner pipe OD and the hose pipe ID, and it is also reduced if there is a pre-existing buckle in the liner pipe. In other words, if it's already buckled, it's easier to buckle it. There are formula available for this. Probably the most well-known is the one created by In Situ Form for its CIPP liners, which found its way into an international standard, ASTM 1216. And we can adapt that by just putting in the material properties for polyethylene, so we can do that. In terms of Subterra's offering, we have, or Subterra has traditionally used a calculation developed by the University of Bradford. It's a very similar format. You need to consider two design cases for buckling collapse. There's a situation where you have maybe a surge or a vacuum event, which is a short-term event, in which case you would use short-term material properties, and that gives you one characteristic. But you also have to think about a situation where you have the liner pipe may be empty, either pre-commissioning or if it has to be drained down for maintenance. And in that case, you'd use the appropriate long-term material property. There are ways of engineering your way out of surge. For interactive liners, there is a question of hole and gap spanning. Again, here, ASTM help us with 1216. That's got a formula in there that can be adapted for polyethylene. Again, Subterra has used some research that was carried out by the University of Bradford for the UK water industry, and that appears in the design manuals for the subline group of products. For gap spanning, I'm not aware of anyone who has, there being a national standard for this, but again, Subterra has this design procedure available in its design manual. Frequently asked questions. I'm getting a bit close to time. I'm hoping that I'll be permitted a little bit of latitude, and I hope I'm making some sense to you. The questions I can remember being asked, and the ones that I want to answer anyway, are how far can you go in one go? What kind of bends can you get round? Does it actually add to the hose pipe strength? And how much does it cost per metre? Well, just roughly, I'll just give us an idea. Right, how far in one go? This is probably the easiest. We saw that the winching in situation, you've got a force that you need to winch the liner pipe in, and that has to be less than the available strength in the pipe. So if you produce that as an inequality, you find out that the maximum length is the only variables in that equation really are the strength of the PE pipe and the coefficient of friction. Well, is that a surprise? But area, notice that area doesn't form part of that. And if you plug in the standard values at the bottom there, you end up with a predicted length of the order of 2.5 kilometres. And I think that's probably what we've seen before. What bends can you get round? That's rather tricky. Slip lining and concentrically reduced liner pipes are the least amenable to getting round bend, and that's because of the stiffness of the cross-section. It's very difficult to get that to urge that round the bend. Folded liners are easier because of that mirror plane that you've got in the liner pipe, and flexible hose liners are the easiest of all. But those rehabilitation contractors who are here will tell you that you try to avoid bends by using those as insertion of winching points. Take them out of the equation. The bend form is important. Long radius bends are the easiest to get round. We're talking about cast iron bends, the old vertically cast iron bends, or hot form steel bends. Short radius or knuckle bends are difficult and best avoided because of the very sharp radius. And steel pipeline bends are fabricated by welding together mitered sections of steel, the worst of all because of the sharp edges you've got to get round and the difficulty of conforming to those bends. Without prejudice, the capabilities, you could probably say slip liners and concentric reduction liners can get round bends of about 11¼ degrees. Folded liners, and that's long radius bends. Same for with factory and site folded PE liners, typically 22½ degree bends, but we're talking about long radius bends. And the flexible hose liners up to 45 degrees has been claimed. Now there are some rules of thumb that can be adopted here. These come from the University of the Blindingly Obvious, but it's easier to get round a cranked pipe joint than a manufactured bend. It's easier to get round a low angle bend than get round a high angle bend. It's easier to get round one bend than get round two bends. It's easier to get round bends that are in the same sense rather than those that are opposed. And it's much, much, much easier if you can locate the bend you want to get round at the end of the pull, so that that bit of friction is limited over a very short length. And the inverted siphons under river, that's probably best left to our friends with the hose liners. Does it add to the hose pipe strength? This is an interesting one. If you think about a close-fit PE line pipe, when you pressurize the lining and the hose pipe, they both expand together. It's an equal strain situation. So if you think about the difference in stiffnesses of the two materials, cast iron or steel is very stiff. Polyethylene is, by comparison, not anywhere near as stiff. If you look at a common strain on that, you'll see that the amount of stress on the PE lining is going to be much less than that on the hose pipe. Now, I did think someone might say, well, you haven't taken into account wall thickness here, so I developed myself a little model and looked at being able to change the pressure and the wall thickness of the PE and the wall thickness of the steel pipe. This is for a 16-bar example. What we have here is the amount of load taken by the PE up the y-axis, and along the bottom is a PE SDR. The curves represent different amounts of fit deficit of the liner inside the hose pipe. But what's interesting is that when you have a really tight-fitting liner, even at SDR 11, at 16 bar, the liner is taking less than 1% of the load. And you kind of think, well, why is that? It's obvious, really. When the hose pipe fails, the PE liner can then strain and mobilise that strength. And finally, and thank you for your patience, how much does it cost per metre? I've been trying to get an answer. I tried to get an answer for this for 15 years and then just left it to the commercial guys. It depends on so many things. First of all, is the diameter or the size of the pipe, because that governs how much material you've got in the pipe. The section length, the average section length is important. The more bends you've got, the more fittings you tend to require if you can't get round them, and that can be very significant if you're talking about some of these large diameter interactive liners. That works better where you have long lengths. The project length itself can be important. Whether you have a one-off short project of 50 metres or a big project of 5 kilometres, because of the influence of mobilisation to site. And I once did an exercise like this for one of my clients, where I looked at the costs of doing a 100 metres compared with 1,000 metres. I think it was a DM 500. The cost for the 100 metres per metre was 3 times that of the 1,000 metres, and that just illustrates the point. The location is important. We saw earlier that if there's, it depends on the frequency of customer service connections. If these are very high in urban situations, there's going to be a lot of additional costs associated with remaking those. And even things like labour rates, national variations can make a significant impact on the competitiveness of the lining technologies. If labour rates are cheap and there's lots of space, in a particular country, it's often more cost-effective just to direct lay. Thank you for your patience. I've now come to the end. This, I hope, is to illustrate some of the technologies available for P lining. Ordinary P lining, slip lining, that's loose-fit P slip lining, is the commonest option. Commonest option, and is always going to be the cheapest option because you're using standard pipe and standard fittings. It is only acceptable like that if you can tolerate the loss of cross-section capacity. There are close-fit liners, and they fall into 2 categories. There's the concentric reduction and the folded type. The close-fit liners can be classified as either structural or interactive, and it depends on the application, and there are design methods available for that. And finally, to make it into a system, there are terminations and connections available. For structural liners, we can use modified standard fittings, that's for solid wall pipe, and for the interactive P liners and other specialist liners, they require the use of dedicated fittings. Thank you very much for your patience. Thank you.
Thanks very much for that, John. In lieu of the, obviously the amount of information and the quality of the presentation, what we'll do, we'll hold the discussion forum that we were due to have after Keith's presentation. We'll hold that till the end, but I'm sure you can appreciate the reasons for that. I have got a couple of minutes for questions. I'm sure there are absolutely loads on that, but I'm quite happy to take a couple of questions from the floor. Or none at all. Yeah.
Sorry, you mentioned anything about the effect of Young's modulus?
Sorry?
Change in length with the change in diameter, if you're sort of rolling down or you're pressurising up.
Yes.
What sort of change in lengths can you anticipate?
It doesn't alter the material properties. The processing certainly, with the concentric reduction processes I think you're describing, even for the folded systems, they will continue to pass the requirements in the corresponding standard for solid wall pipe. Yeah. There is no effective change in the modulus of strength that I can contemplate.
The relative, or allowing for a change in length during those?
Sorry?
Allowing for a change in length
during expansion. Yes, that depends on the individual system characteristic. I guess with the subline DR system, the length extension you would get in the process is of the order of 3%, that sort of order. When it's reverted, it recovers a proportion of that, but only a proportion. And that's relatively easily allowed for. For swage lining, I'm not a specialist on that, and I think there's someone here who may be able to answer that, but the contraction actually is potentially going to be greater because you're maintaining tension on the liner throughout the course of the insertion process. And necessarily there is a relationship between the reduction in diameter and the axial extension.
John's just coming, I was going to clarify. It's conservation of mass. With the swage line, you make it 10% longer, 10%
Yeah.
smaller.
Yeah, you
it comes 10%
you can broadly, because of because polyethylene is effectively an isotropic material with a Poisson's ratio of 0.44. So it's a constant volume problem, as Mike has said, broadly speaking. Although you have to remember that you're going to be pulling the swage lining for a certain amount of time, so that if you're pulling the liner pipe for a significant amount of time, there could be an element of creep which is not recoverable.
Okay, one more question, James.
John, you mentioned earlier concentrically reduced pipe, which is done at the factory, so that you can take it to site and insert it that way. Does that revert over time, or do you pressurise it?
The roll down system, after the roll down process, there is a slight amount of recovery, but it stabilises at a stable diameter. So, as I said in the presentation, it's extruded in the factory at DN155, but it comes to site as a DN144, I think it is, size, and it remains stable at that size. And we've actually checked the dimensions of liner pipe on drums as part of this technology demonstrator, and lo and behold, it actually stays down, so it's very good from that point of view. And then once it's at site, Radius have developed an automatic hydraulic pressurization equipment that will automatically carry out the roll-down reversion as per the standard requirement, our standard requirement, yeah.
Thank you.
Or their standard requirement, I should be.
Thank you very much indeed, John. Right, we now move on to the next presentation in this session. We've already heard from Derek about the structure of polyethylene pipes. We've heard some of the installation techniques there, but obviously a key part of it is actually putting the pipes together, whether they're in coils or in sticks. And probably the world's leading manufacturer of equipment to do that is McElroy. And I'm very pleased to have Keith Mole here today, who's the International Business Manager for McElroy, to tell us more about that. For those of you, I can't imagine there are very many of you that don't know Keith, but he's a past national chair of the Pipeline Industries Guild, and he was also one of the inaugural council members for the UKSTT as well. So lots of experience with trenches technology, and I'll hand you over to Keith.